Here's one question I see quite a lot. Why are quicksort implementations different? The way I learned it once upon a time and hence covered it in my sorting algorithm series is quite different from a lot of other places. Why does it all work, and how can we still guarantee all n log n time complexity? All this and more in today's episode on 0612 TV. Hello and welcome back to another video. Let's jump straight into things by dissecting quicksort to see what stays in common across different techniques. Quicksort is a sorting algorithm with the average case time complexity of O n log n. For each pass of quicksort, there is always a pivot, and through some method, we form two sublists around that pivot. The pivot is in its correct final spot in the sorted list. Everything left of the pivot is less than or equal to it, while everything right of the pivot is larger than it. Technically, the equal value can be in either sublist, but for simplicity, let's just put it on the left. Now, we recursively run this process on the two sublists. This creates a new pivot that is also put into the right place, and again, relative to that new pivot, its left and right sublists are also less than or equal to, or greater than it, respectively. We keep going on until we end up with sublists that are length 1 or 0. This fixes them in place and stops the creation of additional sublists. Once every list item has been fixed, we're done. That is how every version of quicksort works. But what's not common to them is how these sublists are actually created. So let's delve into that. What are we actually doing between the point of picking a pivot and creating the two sublists? What we're essentially doing is partitioning, and you can almost think of it as an algorithm or a function on its own. The responsibility of the partitioning function is that, given a list and a pivot, it somehow rearranges the list in the way we've described. Smaller stuff on the left, then the pivot, then larger stuff on the right. This gives us a new perspective as to what quicksort is doing. Quicksort is really just a driver for a partitioning function. As long as you have a partitioning function, quicksort uses a recursive strategy to call that function, with the goal of solving a bigger problem: sorting. This is abstraction in action. When you're writing partition, ignore the sorting. When you write the sorting, just assume that partition works. We can reason about these two parts of the algorithm separately, so much so that if you plan it well, you can even swap out one partitioning algorithm for another later on. In other words, really, this is all there is to quicksort. Let's take it apart and see if we can't make sense of it. The quicksort implementation here takes in an array, as well as two numbers describing the indices of the array we're interested to sort. In other words, we have the ability to specify whereabouts in the array do we actually want to sort. Both parameters start index and end index are inclusive, and together they specify a sublist to operate upon. Then, we randomly pick a pivot index from the range of indices given. Again, this is within our selected sublist only. We'll discuss more about why we pick a random pivot later on, but a short explanation is that it allows us to be more confident about the efficiency of the sorting run. With the pivot picked, we simply perform a partitioning run. The partitioning algorithm needs to know what the array is, as well as the bounds of your sublist. You'll also have to supply the pivot. Pause. Note that this convention isn't used everywhere. You'll find that in a lot of places, picking a pivot is part of the responsibility of the partitioning function instead of the driver. We do it this way to maintain a separation of concerns. Resume. At the end of the day, the partitioning algorithm must return two things. Firstly, the array modified by the partitioning operation, as well as the new index of the pivot. We need this because the pivot would move and settle into its final position as a result of the partitioning. So we'll make it the responsibility of the partitioning algorithm to tell us where the pivot goes. With this done, we can start thinking about the recursion that quicksort must go through. Let's start with the recursive case. We now have the pivot in the right place and two even smaller sublists that we must continue running quicksort on. Where are these smaller sublists? The first one is left of the pivot. Its left bound is the left bound of our current sublist. Its right bound stops right before the pivot, which is why we take the pivot index and subtract 1. The second sublist starts right after the pivot, that is, the pivot index plus 1. It ends where our current sublist ends. Each one of these is a recursive call. Pay attention to how, as the recursion progresses, the sublist gets smaller and smaller. That's how we are eventually able to stop the recursion. Remember, as described before, quicksort stops when we end with a sublist of 1 or 0 items. With this in mind, we can construct our base case, in which we return the array without modifying it. And with that, our quicksort driver is complete. Now, we can turn our attention to the partitioning methods themselves. There are many ways to perform partitioning, and today we'll cover 3. The first method is a completely intuitive one. You wouldn't want to use this in production because of the additional memory overhead, but I'm including this here to start off because it's simple. Then we'll move on to 2 popular partitioning algorithms that are used in production, one by Nico Lomuto and another by Tony Hoare. So let's jump in. First, the intuitive version. All we want is to create 2 partitions, right? So the easiest way would be to create 2 arrays, one to hold the items smaller than or equal to the pivot, and another to hold items that are larger. We can figure out the pivot value by reading off the item at the pivot index. Then, using a loop, simply run through all the items in the sublist. If we encounter an item smaller than or equal to the pivot, we'll add it to smaller array. Otherwise, it goes into larger array. With the values partitioned out, we can find out exactly where the pivot would go. Start at the left bound of the sublist and move forward by however many items there are in a smaller array. Replace the sublist with all the smaller items, followed by the pivot, and then by the larger array. This completes the process. You can now return the new pivot index and modified array as required. This is nice and simple enough, but it's not used in production because of the 2 arrays you create. They'll take up memory outside of the original array, leading to an increase in what we call space complexity. It is possible for quicksort to be an in-place sorting algorithm. That is, one that requires no additional memory outside of the original array. And the next 2 techniques we'll see will embody just that. Let's now look at Lomuto's partitioning scheme, which looks something like this. Lomuto's partitioning algorithm was originally conceived to always pick the rightmost item as a pivot. Again, we'll discuss why that's not a good idea later on, but for now, we'll take the randomly selected pivot and swap it over to the right, so that the algorithm can continue as per normal. We know this wouldn't break anything because this is an unsorted partition anyway. Now, we introduce the variable I, which actually comes before the start of the sublist. The reason why we do that is because Lomuto's scheme grows the left partition within the sublist, and I keeps track of where that partition ends. Since there's nothing in it right now, the boundary of the partition is set to be outside our sublist. Then, we introduce the variable j, which simply runs through the sublist, stopping short of the pivot at the end. With each element, we check, is it smaller than the pivot? If yes, we swap it into the spot right in front of I. Then we move I forward to include that element. If we see an item greater than the pivot, we simply power through it. It could stay where it is to the end, or it could get swapped away later on. Swapping a smaller item backwards and then moving I forwards to encompass it grows that partition. This works because everything at position I and before is part of the left partition, which are the items smaller than or equals to the pivot. So we run through this loop until we reach the second last element of the array, swapping it if required. The loop terminates and we're almost done. Let's move I 1 spot forwards. Remember, I defines the boundary between the 2 partitions. If we look at where it is now, the smaller partition exists between the left boundary of the sublist up to right before I. The larger items start at I, extending to the end of the sublist -1. Our last step is to put the pivot in place. To do this, we simply swap the pivot, which is at the end of the sublist, with the item at position I. This item belongs in the larger partition, and swapping it further towards the end of the sublist wouldn't actually break this property. With this, we have our answer. Everything is partitioned nicely, and I points to where the pivot is. We now have enough information to return to the caller. The alternative is Hoare's scheme. Again, similar to Lomuto's scheme, this technique uses a fixed pivot, which we'll work around by swapping our chosen pivot into the defined spot. This time, we're growing both partitions, using swaps to get the items into the right place. The pivot should be in the middle of the sublist, and we'll grow out the 2 partitions until they meet in the middle. We'll begin by creating 2 variables I and j, which define the boundaries for the smaller and greater partitions respectively. Both variables start off outside the bounds of the sublist. Then, we jump into a set of loops. The first inner loop moves I forwards, stopping whenever we encounter an item that is greater than the pivot. The second inner loop moves j backwards, stopping when we see an item smaller than the pivot. In other words, we grow out the smaller and greater partitions as far as we can go, until I and j both point to items that do not belong on that side of the pivot. we swap the two items, which puts them both where they're supposed to go. Then the whole process repeats. Both partitions grow inwards as far as they can, once again, before we swap the two elements that are out of place. Eventually, this process repeats until we get to a point where I and j either converge on the same spot, or potentially even pass each other. If we see this, the function terminates immediately, because we know we already have the answer. Note the order of operations here. We do this check, and potentially stop the algorithm before we do the swap, because in this state, we don't want to swap the items. Now, let's pause real quick and take a look at the outcome. You realize that that's not correct at all. Yep, turns out Hoare's algorithm isn't designed around accepting an external pivot, so the way we understand pivots have to be adjusted slightly. In this case, even though we've performed all of our comparisons using a pivot value of 6, we end up partitioning the list around the value 5 instead. The algorithm isn't wrong, we've just fixed a different value in place. Regardless, if you prefer a predictable pivot, that's easily doable. Swap our pivot with the first item in the sublist. Then, instead of having I start at start index -1, we'll put it at start index instead, effectively ignoring the pivot. The rest of the algorithm proceeds as usual, which will lead to I and j converging upon some index. This index is where the pivot should go. Swap the item at this index with the pivot, which we have tucked away nicely at the beginning of the sublist. All is well again, the pivot is where it's supposed to be, all items to the left is smaller, all items to the right are larger. In the grand scheme of things, the differences between these approaches to partitioning is subtle. Whether we explicitly build both partitions, or if we build one and then infer the other, we end up with a properly partitioned list. Do note that the results from these three techniques aren't guaranteed to be the same, only that the desired properties won't be violated. With this, we can safely allow Quicksort to drive the partitioning algorithm recursively to sort our list. Let's briefly discuss time complexity. In all three partitioning strategies discussed, I hope you can see that we are essentially making just one pass through the input array. For Hoare's algorithm, we're not going left to right, but rather outside to inside. But that doesn't change anything, each element is still processed once. That makes partitioning O(n). In the worst case, we perform one swap per element. That adds up to a constant number of operations per element, which doesn't scale with n, the size of the list. Hence, this doesn't factor into the time complexity. Even for the naive solution, which requires one more pass to copy answers back into the original array, that incurs an additional O(n) time, but that happens after the original loop. We do O(n) steps, then another O(n) steps for n plus n time, which still works out to O(n). Which means, yes, our naive solution is more expensive from a memory point of view, and yes, it does perform more steps, but under the big O notation, it doesn't fare any worse than the two other algorithms. With that, we can also analyze the time complexity of Quicksort. In the best case, Quicksort executes a perfect divide and conquer strategy on your data. If you're familiar with binary trees, this pattern should be very familiar. If you keep partitioning n items into two equal halves, you end up with individual items with log n steps. At each level of partitioning, you have double the number of partitions, but each of which half the size of what comes before. Since we know each level of partitioning adds up to O(n) work, split up across however many partitions, and we know there are log n levels, we can conclude that we are doing O(n) work log n times, which works out to O and log n in the best case. Of course, we have to consider the worst case scenario as well. Remember, that happens when we fail to make partitions for each step, thus creating a partition of size 1 on one side and a partition of size n-1 on the other. This typically happens when the pivot is consistently chosen to be either the largest or smallest value. So one partition is empty and the other contains everything else. We've practically not done any partitioning, we've just picked up one value and moved it to one side. If this happens for every single partitioning step, we'll need n partitioning steps before we are done. And if each step takes O(n), that adds up to O(n) squared. Take careful note of who is responsible for this problem. The partitioning algorithm is only in charge of creating a partition based on the pivot and the data it's given. If it fails, it's because it's given a bad pivot. In other words, the responsibility is that of the underlying driver, which is in charge of choosing a pivot. So, Quicksort must do its best to avoid this scenario. A naive approach to picking a pivot would be to simply pick an item at a fixed index, say the first item, last item, or whatever. If you give Quicksort a sorted list, this strategy will fail, since it will always pick the next smallest or largest value as the pivot. We work around this problem by picking a random pivot instead. While you can still be super unlucky and get a bad draw that gives you O(n)² time, the likelihood of that is far lower. If you want to go further to avoid this possibility, you can even pick the median value for use as a pivot, though computing that median doesn't come for free. There you go! Hope you now have a more complete impression of how Quicksort works. You're just recursively partitioning a list into two, so really any partitioning algorithm works. That's why there's so many variants to Quicksort. That's all there is for today's video. If you have any comments, queries or suggestions, feel free to leave a comment in the comment section below. But until next time, you're watching 0612 TV with NERDfirst.net. Thank you very much for watching. If you liked this video and are feeling generous, a donation to this channel will be greatly appreciated. There's a link on screen and in the video description for more details. Meanwhile,